Trigonometry, Chapter 7, Applications of Trigonometry Vectors, Section 2, The Law of Cosines. Video 1, The Law of Sines versus SAS, side angle side, and The Law of Cosines. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous section, we learned about the law of sines. In any triangle ABC, we have sine of A over A equals sine of B over B equals sine of C over C. Now, in order to use the law of sines, we must know a complete angle side pair, such as side A and angle A. In this video, we explore what happens when we do not have a complete angle side pair. Specifically, we will investigate the scenario where you have two sides and the included angle between them, SAS. For example, let's say we're being asked to solve triangle ABC. If side A is 12, opposite angle A, side B is 20, opposite angle B, and angle C is 35 degrees. Well, notice we cannot solve using the law of sines. Here's what we currently know: side A, side B, and angle C. So we have no complete angle side pair. None of those ratios have all the values known, so it's impossible to use the law of sines to get a value. Well, now what? Well, we need a new tool, and that tool will be called the law of cosines. Now, I could just tell you what it is, but what fun is that? So we're going to derive it. And in order to derive the law of cosines, we need to use analytic geometry. In other words, geometry on a coordinate plane. Forgive the grammar error here. Let's begin by placing a generic oblique triangle ABC on a coordinate plane. This image is courtesy of Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. Now we orient this triangle so vertex B is at the origin and segment BC is on the positive x-axis. This will place point C at A, 0, since the length of BC is A. So over A up 0 puts us at C. Now, because angle CBA, or angle B for short, is in standard position, initial side on the positive x-axis, point A is on its terminal side, and the distance from the origin to A is lowercase c, then we know the coordinates of point A are C cosine B, C sine B. That's just back from circle trigonometry. We will derive the law of cosines by applying the distance formula to segment AC, whose length is B. Notice we have representations of the coordinates of the endpoints of that segment. The distance formula says the distance between 2 points, which is B, is equal to the square root of the sum of the squares of the differences in the x-coordinates, so first x-coordinate minus second x-coordinate, and the difference in the y-coordinates, so second y-coordinate minus first y-coordinate. Now we're going to take this equation and manipulate it some. Let's start by squaring both sides to get rid of the square root. Looks a lot like the Pythagorean theorem, not an accident. But now we're going to square this binomial. We could write it twice and FOIL it out, but if we do, we would get c squared cosine squared b minus 2ac cosine b plus a squared. And of course, if we distribute the square root of this product, we have c squared sine squared b. Now this looks like a mess until you notice that the first and the last terms have c squared as a common factor, and the uncommon factors are cosine squared plus sine squared. So if we were to put those two together and factor out the c squared, we would get cosine squared plus b squared and then put all the other terms at the end. But wait a minute, cosine squared plus sine squared is 1. That's a Pythagorean identity, a fundamental trigonometric identity. So this is c squared times 1, which is just c squared. We're going to make one last minor adjustment. We're going to take this a squared and move it in front of the c squared to give us b squared equals a squared plus c squared minus 2ac cosine b. And that is a version of law of cosines. Now, there's actually 3 versions, which is really just one version. The other 2 are obtained by permuting the variables, since our choice of variables was arbitrary in the original diagram. If we had put A At the origin, we would have gotten a squared equals b squared plus c squared minus 2bc cosine a. If we put c, angle c at the origin, we would have gotten c squared equals a squared plus b squared minus 2ab cosine c. So while all three of these are correct, it is a little excessive. That's why I prefer the following perspective, which is independent of which sides and angles are labeled with which variables. Just like the law of sines or other things, the actual variable names are irrelevant. It's a relationship between them. So let's focus on the relationship between the variables in all three variations of this. Observation number one. In all of these, the squared variable by itself on the left of the equation is the side opposite the angle inside the trig function. So for example, side A is opposite angle A, side B is opposite angle B, and side C is opposite angle C. So the first and last letters in any of these match. The one on the left is a side, the one on the right is an angle. Observation number two, the two squared variables on the right side are the same variables as in front of the cosine, and they are the adjacent sides to a given angle. For example, on the first one, for angle A, the adjacent sides are B and C, which is the sum of the squares up front and the product in front of the cosine after the two. On the next one, for angle B, the adjacent sides are AC, which are the variables in the sum of the squares and the coefficient of the cosine. And the same thing for angle C, whose adjacent sides are A and B. Now, as a consequence of these observations, we can summarize all three versions of the law of cosines with the following version that captures the relationship between the variables, plural, without focusing on the specific letters used. The law of cosines. For any angle in a triangle, the following side is true about the side opposite that angle, labeled OPP, and the two sides adjacent to it, labeled ADJ1 and ADJ2. The square of the opposite side of the angle is the sum of the squares of the adjacent sides minus 2 times the product of the adjacent sides times the cosine of that angle. So just like the Pythagorean theorem could be a squared plus b squared equals c squared, although I prefer leg squared plus leg squared equals hypotenuse squared, the law of cosines can be expressed in terms of who is opposite and who is adjacent to a given angle. One last comment. The law of cosines is like a generic version of the Pythagorean theorem. In fact, if the angle in the law of cosines is 90 degrees, cosine of 90 degrees is 0, and this term vanishes, and the law of cosines collapses to the Pythagorean theorem. So as such, sometimes I call this part highlighted, the minus 2 adjacent 1 adjacent 2 cosine of angle. Sometimes I call that the adjustment factor. It adjusts the Pythagorean theorem, the unhighlighted part, to accommodate for a non-right angle. Now, there is no now you try for this video. Instead, memorize the law of cosines, choose your variation. You can remember the standard three versions that have A's, B's, and C's, or you can remember the singular version, which expresses the relationship between an angle, the side opposite it, and the two sides adjacent to it. So choose which one you prefer.